So officially, let's begin. Right. So there with the beautiful sunset that we are not participating in, where I am. I'm in Bristol. It's 12:30. I was about to say it's completely overcast, but the sun just broke through. It's mostly overcast with a little bit of sun. So wherever you are, whatever your time zone is, I hope that your weather is not too good, because, you know, you don't really be indoors if the weather's really nice. Unless, of course, you are watching this sitting out in the garden or outside somewhere pleasant with an iPad and a refreshing drink, preferably a strong one. So what are we going to talk about? What we are going to talk about is this. We are going to talk about the structure and interpretation of test cases. So my name's Kevlin Henney. I'm an independent consultant and trainer. I've worked for myself for quite a while, many years, and I have an interest in a number of things, from the kind of broader scales of architecture down to the fine detail of code. I also have an interest in coffee. So I got this one at Code Dive in Poland at a C++ conference about 4 or 5 years ago. Phil's just mentioned strong coffee. So yeah, this is a double espresso, that kind of after lunch vibe. And this is a very dry title for a talk. There's a reason it's like this, because I'm playing on the idea of the title of this kind of computer science classic, Structure and Interpretation of Computer Programs by Abelson and Sussman. And that's a book written in Scheme. It's very computer sciencey and all the rest of it, written in the early 80s. That's not what we're here for. We're going to talk C++, we're going to talk testing, but I want to use this as a motivating point, because it is often an observation, and we keep having to restate this every few years. It needs to be restated. People, the relationship between people and their code. Programs must be written for people to read and only incidentally for machines to execute. Clearly, sometimes getting the compiler to accept your humble offerings can be a bit of a struggle. But ultimately, the thing that makes the difference is whether or not other people are able to pick this stuff up, whether you can socialize your code, whether they have understanding of meaning. And it is very easy to get trapped into a view of, hey, I'm the developer. Of course, I understand what I mean. This code is for me, and use various excuses. And I see this a lot. Doesn't matter what the programming language. I see this coming out in a lot of programming languages. But I do find that many C++ developers have a tendency towards the cryptic. It's just like, oh, well, yeah, everybody knows this. No, they don't. That's the first thing you need. That's your opening shot. When you are communicating something, when you are writing tests, not everybody does know that thing that you think is incredibly obvious. Tests are an opportunity for communication. Tests are not, and people very much cram tests down in a very simple kind of way of looking at things. And so we need to move away from this simplistic idea. And this is particularly important in the C++ space, which has not kind of received the kind of care and attention that many of the other languages have. And likewise, the culture, C++'s culture on a testing front tends to drag behind a number of other languages. I remember it was around 2005. I was at a conference in Las Vegas, C++ Connections, and I ran a session on unit testing. Test-driven development. I'm not going to be focusing on TDD today at all. My focus here is on the tests themselves. I ran a session and I said, okay, who here writes tests for their code? Who here writes unit tests? And there were 30 people in the room. 2 people put their hands up. One of them was me. The other person was John Lakos, who has finally published the book that he was threatening to write in 2005. He showed me an early draft in 2005 on large-scale C++ software development. Or rather, he's published the first volume of that. It only took 15 years. But, good things come to those who wait. So the only 2 people who were writing tests were the 2 people who were known for doing testing. That was it. The same year, I did a talk at a Java conference. When I asked the same question, 2/3 of the hands went up. So C++ is still suffering from a disadvantaged position, and many people still think, oh, I write tests in C++ so I can show my code works. That's kind of, yeah, that's really kind of 1980s perspective. I think we need to move on. You are writing your test as an act of communication. So let me pick up from a piece in 97 Things Every Programmer Should Know, which is a book I edited just over 10 years ago. And in it, Gerard Meszaros wrote this piece, Write Tests for People. Gerard had previously written this storming great book on unit testing patterns. It's about 900 pages long. You can use it as a weapon if you wish. It's 900 pages is pretty hefty. That's a certain amount of tree to that. Convince your colleagues through the sheer weight of the book. But I managed to get him down to 2 pages. Write tests for people. There you go. It's in the title. The clue is in the title. You are writing tests for other people to read. You are not writing tests for the build system. You are not there to satisfy a build. Yeah, of course, that's part of the thing, but it's not the whole thing. That's not the most important thing you're doing. Who should you be writing the test for? For the person trying to understand your code. Specifically, what we're saying here is your production code. You're not writing tests for the people who are reading your tests. You are writing tests for the people who are reading your code. Good tests act as documentation for the code they are testing. That's a really key idea. They may not be the only documentation, but they are part of the documentation set. And that's the way of thinking about stuff, is everything that you do is an act of communication. The naming of your variables, the naming, the structure and indentation of your code, your adoption of convention or your contradiction of convention. Sometimes we need to go against convention. Just because lots of people do something does not mean it's a good idea. Always remember that. That doesn't mean ignore all convention, but just remember Hungarian notation was always a bad idea. It was demonstrably a bad idea, even when it was popular, but lots of people justified its practice by saying, well, lots of other people are doing it. It's, do bring a bit of intelligence to the table. But the point there is convention allows us to communicate things. It's for other people. Software development, unless you are just doing some basic programming, hobbyist programming, or exploring something for yourself, pretty much most software, it's a team sport, and you need to think about other people. You are not just telling people, here is code, and I believe that it is correct. We're not just demonstrating some confidence and correctness. What we're actually doing is communicating to other people. This is what I mean. This is what I think correct means. We are communicating our assumptions. We're clarifying what we believe. That means that somebody else can come along and go, yeah, that's not what I understood by this. Or, that's changed. Okay, that's moved on. This is no longer true. Or that's an interesting interpretation. My interpretation of that requirement or this context was different. Or what was said in the meeting, what the architect said, what the product owner said, my interpretation was different. But what you're doing is you're playing an open hand game. Card games can be played closed hand, other people don't see what you have, or open hand, or a mix of the two. You want software development to be an open hand game. You want to show your hand as you are playing it, so other people can see, okay, I understand where you're coming from. That's not what I thought, but I think I understand where you're coming from. And that is the challenge. It's the sociological aspect. It's not the whether or not something passes or fails. But that does also present us with another challenge. How do we talk about this stuff? Now, lots of people kind of get wrapped up in talking about test-driven development. I think there's a lot of good stuff to say here, but I'm not going to say it. That's not what I want to focus on today. I want to focus on this other aspect. A lot of people confuse unit testing with test-driven development. There are 2 aspects here. Unit testing is one of a number of different practices and workflows that focus on unit testing. Okay, unit testing is a broad category. It may involve TDD. It may involve plain old unit testing. I write my code first, then I write all of my tests. Or you might be doing iterative test last. In other words, I write a piece of code, I write a test case, I write a piece of code, I write a test case. Test-driven development, I write a test case, I write a piece of code, and so on. Or defect-driven testing, DDT. Used for killing bugs. I may respond to something by saying, oh, there's a bug. Oh, let's fix it. Don't fix it. There's a bug. Let's write a test, one or more tests that fails because of the presence of the bug. Right, now it fails. When I fix it, I have recorded in a traceable fashion the new knowledge that we have, but it is now this fixed this. We now have a demonstration. We have evidence of fix rather than just good words and signing something off in Jira. But that's still not focusing on communication. I've just told you a workflow. What we need is good unit tests. We need to distinguish between the flow, the act of how we create, and the thing that we are left with. When somebody looks at the code that you've got, when they look in the repo, they don't see TDD. They don't see plain old unit testing. What they see is something that they will judge as like, is this any good or is this not good? You can produce crap using a test first cycle if you're not paying attention. You can produce great stuff producing with a test after cycle. The point here is, what do we mean by good unit tests? It's not the same as test-driven development. That is a way, and this is the target. So we need to focus on guts. That's great. Let's start off with the basic minimum. Okay, the basic minimum, apart from the idea of course, we automate our tests. We write code to test code. Something I've got in an unpublished blog, so I can't offer you the full link, I'm afraid. A bare minimum definition of what we mean by good tests is that when the code is doing the right thing, the tests pass. Okay, that's a really simple idea. You'd be surprised how many tests don't meet this. And when a test fails, it means the code is doing the wrong thing. Now, read that carefully. Do not fall into the trap that sometimes people do, saying, oh, if my tests pass, it means my code works. No, it doesn't. If my tests pass, it increases my confidence that they work. But you cannot you can only test for the presence of bugs, not their absence, to quote Dijkstra. If your test pass, that doesn't mean your code works. It just means the probability that it works is higher, and we can demonstrate more confidence. If you have no tests, then I can demonstrate to you, logically, that your test will not find bugs. You cannot demonstrate confidence in absence of bugs. But the more tests I have, the more confidence I can have about claims as to the quality of my code. Okay, so that's fine. If your tests pass, that doesn't mean your code works. But what we do want is, if your tests say this does not work, then that has a single unambiguous interpretation. It means this does not work. This is where many tests fail. They are brittle. In other words, they're coupled to implementation assumptions. Sometimes that's exposing internal details that really shouldn't be exposed, such as over-mocking. Sometimes it is about a consequence of an implementation. You just happen to generate a particular value or a particular string at one particular point, and then you decided to assert that the result of a particular operation was that particular value. It's like, no, it could be anything. So there is this idea of don't overcouple to implementation assumptions. So when we make a change to the code that is a refactoring change, the test should pass, because otherwise it's not a refactoring change. In other words, refactoring means it's semantically compatible. If your test fails for a semantically compatible change, what it means is that your test was too strong. You coupled to details that were not relevant to the usage. Okay, it's like with three-way comparison, for example. Let's leave aside the spaceship operator at the moment. Let me talk classic three-way comparison using an int, something like strcomp. Three-way comparison. Many people assume that three-way comparison, if this is greater than this, then you return +1. If they're equal, 0, lower than -1. That is not correct. The correct interpretation is, if it is greater than, it is positive, 0, negative. +1 and -1 happen to be common examples of the positive and negative, but do not assert that your three-way comparison returns +1 or -1. Assert that it returns greater than, because when I change the internal implementation and it returns me something that is not +1 or -1, but it's still positive or negative where it should be, and your test fails, what we've learned is your test was wrong and always has been. The fact that it passed was a coincidence or dependent on an implementation assumption. So what do we mean by unit test? Again, people have got lots of ideas about, well, unit test is a test on a translation unit. It's a test on facilities offered by a header file. It's a test on a class. It's a test on a namespace. It's a test on a module. It's a test on a function. That's great. There's all these wonderful definitions. The fact that all of these are, in some sense, units doesn't help us. The term unit testing has been around since the 1960s. It applies across multiple paradigms. So the key thing we should learn is it's not dependent on programming language structure. There is no true definition, but what we have started converging on is a set of definitions that are, if you like, useful. They tell us something about the structure of our code. So a long time ago in a galaxy far, far away, when I used to write technical columns for the Register, I wanted to clarify this. What are your units, basically? And I summarized what I was seeing emerging from the Agile space when people talk about this. What is a way that we can talk about our tests meaningfully and helpfully? If we can't have the perfect definition, can we have a definition that is useful and offers us meaningful feedback on the structure of our code and our design? That's what I want. I want feedback. I want it to be meaningful. I don't want vague stuff like, oh, it's about tests on a class, because that's not particularly helpful. When I have most of the things in a system with classes is that you break things down into smaller classes. Does that mean that a class using another class, is that no longer a unit test? Or is that, instead of arguing this stuff, focus on composition. It's on some amount of code that is organized in some way, but where we have a simple idea that satisfies that first observation about a good unit test. If it passes because of the code of the test and the code that is under test. If it fails because of the code of the test or the code that is under test. In other words, sometimes things fail because actually you wrote the test wrong. Fine, yeah, you're human. There's no emphasis here on perfection. Sometimes people say, yeah, but people writing tests might still make mistakes. Well, of course. We're not solving that problem. We are not solving the human condition. What we're doing is we're changing the probabilities. Okay, that's what all of these any practice anybody ever comes up with is about shifting probabilities. It's not about eliminating practices, especially if they are human behaviors. So what we're looking at here is a simple idea. My test only fails because of code. That is what I've written on the screen, but using other words. A unit test is a test of behavior whose success or failure is wholly determined by the correctness of the test and the correctness of the unit under test. That means, by definition, that your code does not depend on threads. It does not, so therefore it does not depend on threading order. Okay, it does not depend. So the question I often get is, how do I unit test threaded code? Well, if your test encapsulates the threading behavior and the behavior is hidden, then any unit test will do that already. If you are trying to unit test across threads, then no, that is not a unit test. That is an integration test, because it can fail, it can pass or fail for reasons that are nothing to do with the correctness of your code. You can have perfectly incorrect code pass, and sometimes it will intermittently fail. Okay, why? Because of the scheduler. Unless you are writing the OS scheduler, that is out of your control. You're touching the file system. Guess what? You don't control the file system. You influence it, but you don't control it. Environment variables, registry, network, database, time, date, anything that is a system service, every single one of these is outside of your immediate control. Okay, so another way of looking at this is to kind of borrow from the philosophy of the Stoics. The philosophy of the Stoics is very much that work out what is external to you. That is beyond your control, and control the things that you can influence. And this definition allows us to take our code and divide it into three groupings. The three groupings are: here is the code that is unit testable. Then there is a whole set of code that is necessarily not unit testable. This is good. Okay, let's be very clear. We're not using the term unit test to mean good, and therefore things that are not unit testable are bad. That is absolutely not what we're saying, but I sometimes hear people saying that. Necessarily not unit testable. It means, by definition, this code's job is to touch the outside world. Its job is to get stuff from a file. There is a piece of code somewhere that is going to get that thing from a database. It's going to look up in the registry. It's going to do that thing that involves the outside world. That's fine. You can test it. It's just not unit testable. It means it may fail even when the code is correct. Okay, because the outside world is incorrect. That's what we're saying. These two categories are good. Oh, by the way, before anybody asks, no, mocking does not solve this. Mocking, if I want to test my dependencies using mocks, my external dependencies using mocks, but that doesn't test my code against the outside world. That tests my code against my idea about the outside world. Do not confuse what's in your head with what's out there, okay? Okay, this is a sort of a basic point about life, but it also applies in code. Just because you test it against your idea of the file system does not mean it will work against a real file system, okay? Do not confuse reality with the things in your head. Right, this is the category. This is what we want. There is a bunch of stuff that should be unit testable but isn't. That's our problem category. Transitive dependencies that cause this. A good code base, a well-factored code base looks a bit like this. There's a minimal amount. Sometimes people would like to reduce this to 0. Yeah, sure, but let's recognize the human condition and the dynamics of a real code base. There's always some amount that we could probably improve, and that's fine. We accept that. A legacy code base looks a bit like this. Yeah, there's a whole load of stuff that really should be unit testable, but it isn't. Now, another aspect of unit test, we want to talk about coverage, but people get this whole conversation confused. Martin Fowler observes, from time to time, I hear people asking what value of test coverage, also called coverage, code coverage, they should aim for, or stating their coverage levels with pride. Such statements miss the point. Brian Marek observed that he expects a high level of coverage. Sometimes managers require one. There's a subtle difference. You need to distinguish between these 2 points of view. So I run a page on Facebook, Word Friday, where occasionally I focus on an interesting word. One of the words or phrases that I focused on a few years ago was Goodhart's law. Once a metric becomes a target, it loses its meaning as a measure. Okay. Once you start making an observation, it's valid to have an observation on coverage. But once you start setting goals about it, then in the words of Charles Goodhart, an economist, he said, any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. Watch out for this. You get what you measure, but sometimes if you're not careful, all you'll get is what you measure. And people have a very vague way of referring to it. They talk about coverage. They don't actually mean coverage. In fact, Martin Fowler falls into the same trap in his piece. What most people mean is statement coverage. Coverage is a general category, okay? Coverage is a category of many different things. There is statement coverage. That's what most people are referring to. There's a whole load of other coverages that are also achievable. Function coverage, branch coverage, loop coverage, condition coverage, multiple condition coverage. The list goes further up and it also continues down. But then there's a whole load of stuff that is actually not achievable. Path coverage, all the branches is all the edges, as it were, through a particular function. Path coverage is all the possible paths through your function. If you have a loop, then this will be different. If you have a loop that can execute 1 million times, anywhere between 0 and 1 million times, then that basically means you have 1,000,001 possible paths through that loop. You do not have to test all of these because you will never be able to test these. Parameter value coverage. If an int has 32 bits, then there are 2 to the 32 different ways of calling that. You are not going to get 100% coverage of that. So do not use the word coverage on its own. Make it clear. Statement coverage is the simplest. 100% is what sometimes people aim. Honestly, 100% statement coverage is trivial to get. The only people who ever talk about coverage are the people that don't do TDD. I said I wasn't going to talk about TDD, so let's leave that rant to one side. If you are doing TDD, you are normally running at 100%. It is not a challenge. 100% is your minimum. It's not, and you say, well, hang on, isn't 100% all you can do? That's the problem with statement coverage. People think that 100% is the ceiling. No, it's not. You can have code that has 100% statement coverage, and it can still have, less than 20% branch coverage. People think 100 is a stopping condition. No, that's where you start your really good tests, okay? It's an inversion. The only reason people care about statement coverage is because they are normally dealing with code bases that have lacked tests. In other words, they weren't written in a test-driven style or with careful attention to coverage. So coverage is for people that don't use practices that encourage coverage, yeah? Benefits of, but I don't want to diss statement coverage completely. I want to say it is a level. It's just a useful starting level. But once you have it, and if you are operating at a very high level, then any deviation from it tells you what you've got is dead code. And what do you do with dead code? You find it, you delete it. That's what you do. This is feedback on our code. We're feeding back about dependencies, and we're feeding back about what is actually useful. Now, when we come to think about things like different practices, this is one of the other areas. They did actually do test-first programming for awk. If you're familiar with the awk programming language, Alfred Aho, recent recipient of the Turing Award, he talked about the fact that awk was developed using a test-first approach in the 1970s. We instituted a rigorous regression test for all the features of awk. Any of the three of us who put in a new feature into the language first had to write a test for the new feature. They did this so they had high feature coverage and they also had high statement coverage. They did this after a particular episode where they discovered, actually, we don't really test this stuff. So in that sense, if you like, you're always overreaching. You're always going for 101%, or if you're a football manager, 110%. Okay, now what does that mean? There's a couple of observations here. One from Phil. Exception paths in particular can really add a lot of extra untested paths. This is and sometimes people don't like to test that, or they don't think of testing it, because normally when you arrive at code, you are, when I call a function, my goal is to get a result. I call that function for a purpose. I don't call that function in order to get an exception. I call a function in order to make a connection to get a value. I'm not calling it to cause a failure. So therefore, it's natural that my bias is towards that, which is why we bias towards the happy day. So let's look at time. Let's look at things that exist in time. I'm going to use an example I've used for a number of years because it's still quite revealing. Even when I use it now, I still get people sort of say, oh, yeah, but that's a really simple example. And then they demonstrate that they have not yet fully mastered it. It's such a simple example that it's easy to overlook its importance. Once you've understood how to test a leap year function, I'm going to say you've understood about half of what you need to know to write good unit tests. Okay? Most people don't understand how to write this. So let's use Google test. So a leap year, let's determine whether or not a year has a 29th of February. So using Google tests, yeah, well, maybe we'll start off by saying it's a test. Oh, okay, we've repeated ourselves. You don't need to put the word test, no matter, unless your framework is using an introspective approach, which by definition in C++ it can't. We don't yet have a reflection mechanism in C++. But in languages where that exists, if you're a Python user, you'll know that unit test or something better like PyTest require TEST as the first four letters of your test method. That is your indicator. In C++, we do metaprogramming via a different mechanism. In other words, compile-time metaprogramming. Yes, we are talking preprocessor. And here we already have something that tells us it's a test. Okay, so how should I name my test? Oh, I tell you what, test is leap year is okay. Oh, I see this so often. Or this, or this. You're going to test that something works. Brilliant. Would you write a test for something that doesn't work? You know, in other words, are you telling me, are you delivering any useful information to the reader? Write tests for people. Of course, that's what you're testing for. You know what? It turns out naming is hard. Turns out that sometimes we reach for this idea of going like, oh, well, test that this thing works. Test that it's okay. That's not the challenge in testing. The challenge is to communicate what you mean. When I look at a piece of code, if I join a new project, let's say on Monday, if I start up with a team, my first question is not going to be, it's going to be an assumption. Hey, by the way, does your code work? What my real challenge is, what does it mean that it works? When we say it works, when we say is correct, when we say is okay, what do we mean by that? What are you expecting is leap year to do? It turns out most people don't know. We also don't want to ram all of the cases into one place. So sometimes people go, cunning, what I'm going to do, and yes, by the way, this does work, having a raw identifier there because of name concatenation. Maybe I should have multiple test cases. 1, 2, fantastic. No, not fantastic. I don't know what these mean. What's the difference between 1 and 2? At this level, let's leave out the body of the test. What's being communicated to me? Not a lot. I have the first test and I have the second test. Okay, let's be more specific. What about testing leap years and non-leap years? Oh, okay, now we're getting warmer. Now we are actually showing that we might understand and therefore can communicate what it is that we are building. Communicate your understanding. There are leap years and there are non-leap years. Also known as common years, if you want to really get into the domain. I'll just leave them as non-leap years. Leap years and non-leap years. Therefore, we are dealing with something that classifies and differentiates. Okay, that's fine. That's It's a clue in the name. What I'm going to do is I'm going to organize my data, leap years and non-leap years. So I've got two cases here. 2020, last year, the year that everybody wants to forget, although 2021 is also making a good bid for that. That was a leap year. So last year had an extra day. In fact, it had a whole extra few months. In fact, possibly, I think we might still be in 2020. It has a whole extra year. 2000 was also a leap year. The problem is that the reason that 2000 was a leap year is actually different to the reason that 2020 was a leap year. We've merged two things from two different categories together. Oh yeah, sure, they're both leap years, but they are leap years for different reasons. And is that visible in our code? No, not at all. You see, a lot of people think that a year is a leap year if it's divisible by 4. That's actually not correct. It used to be correct. That was the Julian year calculation. But the Gregorian year calculation is more sophisticated. 2000 is an exception to the exception of when a year is a leap year. Let's see if we can make this a little more meaningful. So this might be your next instinct. Let's try this. 2020. So I've got four different kinds of years. There are 4 different kinds of years. The leap year, there are 4 different kinds of years, not 2. Leap years, non-leap years. And I've chosen one data example from each. The problem is, or I've not really told you an awful lot here. I've also confused you because I've said, is leap year 2021? Notice I'm naming it after the data, but I haven't given you the outcome. This is not a leap year, and nor is this. Okay, we need to be more specific. Specific is the first few letters of specification. 2020 is a leap year, 2000 is a leap year, 2021 is not a leap year. Now we're being more specific. But the problem is perhaps we've been overly specific. We have nailed the structure and naming of the test to something incidental, which is example data. The test should communicate intention. Okay? In other words, everything I've got on the screen, the following would also be valid. But now I have to change the names because I changed the example. It's like, that's not really the way to think about it. What is it you're trying to say? Don't confuse the example with the specification's intention. A year divisible by 4 is a leap year. That's a better approximation. A year divisible by 400 is a leap year. That is also a better approximation. A year not divisible by 4 is not a leap year. A year divisible by 100 is not a leap year. This is getting better. So let's group that, give ourselves a little more space. Let's reorder it because it's an arbitrary order at the moment. People often think of, oh, divisible by 4 is the first category, and then they jump around. Let's move this from the largest category. Most years are not divisible by 4. In other words, 75% of years straight out of the gate are not leap years. So I'm going to start with the largest category and move inwards. What is the most common category? Now, I'm not saying that that's the right order. I'm just saying have a rational ordering. Either start with the most specific category, start with a failure case, or start with the most general category. Don't start in the middle. I don't care how you write it, but the order in which you present it. Remember, you're writing for a reader. The order in which you write it is not necessarily the order in which somebody wants to read it. So you reshuffle your test to make a sensible story. And now we've reshuffled it, we can realize that there is a fault in our explanation. A year not divisible by 4 is not a leap year. Yeah, that works. A year divisible by 4 is a leap year. Okay. A year divisible by 100 is not a leap year. Okay, we have a contradiction. All years divisible by 100 are also divisible by 4. So these two statements cannot be true. Okay? Either a year divisible by 4 is a leap year or it is not. Okay? Years divisible by 100 are not, but they are divisible by 4. So a year divisible by 100 is a leap year and is simultaneously not a leap year. Schrodinger's year. Okay. Clearly, what we've learned is years divisible by 4, but not by 100. Okay, right, got it. In other words, clarification. When you understand this, you understand that test naming is not just labeling. Test naming is a refinement of your understanding and communication. Developers often really struggle with this. The idea that what you're doing is you are learning, writing tests is, put another way, is learning to talk about your code. We are learning how to talk about leap years. Okay, so we've now got meaningful categories. Now, this is Google Tests, so I'm going to switch a couple of things around. I'm going to switch the structure around. because Google Test will group tests by the first part. So in other words, Google Tests have a two-part name, and they will group in their output by the first part. So what I'm going to do is I'm going to group together. I want the first part. A year is not a leap year. In other words, the conclusion, a year is not a leap year. I want it to group by that. So years that are not leap years and years that are leap years that will group together in the output ordering. So and so I restructure it so that the sentence reads: a year is not a leap year if it is not divisible by 4, as opposed to a year not divisible by 4 is not a leap year. I do it the other way around. I start with a conclusion and then I tell you why we're there. The style that we have used here is showing my age. This is one of the books I learned logic from. I say showing my age because people don't publish books with this kind of typeface anymore and this kind of cover. But it's about propositions. We are using a propositional naming style. Our propositions are logical statements about our code that we aspire for our code to be true. And this is the benefit that we are focusing on indicative statements. Sometimes people like to put the word should in or must, or there's a bunch of other styles. I'm not a big fan of these styles, but as long as they contain the same information, and these typically do, they get us away from this idea of test is leap year or test is leap year is okay. As long as they move us in that direction, they're all good, okay? So given this, let's tidy up some names here. And let's see another advantage of the propositional naming style. So let's just drop away the underscores. So if you don't already use snake case for your tests, please use snake case. Regardless of what the coding convention is elsewhere in your code base, in your test base, it helps to use underscores because we are dealing, propositions are sentences. They are not noun phrases or verb phrases. They are sentences and they will be long. It's okay for them to be long because you're not going to use them. You don't type them again. They're not called anywhere. They don't need to be refactored because the testing framework will automatically pick that up. But we'll come back to that in a moment. I want to point out another advantage. Let's put a simple implementation here. Simple universal Gregorian calendar. By universal Gregorian calendar, I mean that the Gregorian calendar has existed for all time and for all years that are accessible within an int, okay? And we know that's not actually how the Gregorian calendar went. It was introduced in the late 16th century and then enjoyed an incredibly slow rollout for the next 3.5 centuries. If you want to really do this, then it's a locale-based problem, and I invite you to do that as your homework. But we're going to keep it as this is a universal and eternal Gregorian model at this point. So what happens when I present this code to my test cases? It passes. That's great. What happens when I use a Julian? When I use the Julian calculation? It fails. In other words, the name reflects the capability or the absence of capability. When a year is not a leap year if it is not divisible by 4 passes, I have some confidence that that statement is true. When a year is not a leap year if it is divisible by 100 but not by 400 fails, then I should have, if it's a good unit test, I should have absolute confidence that that statement is not true. In other words, what we're saying is a year is a leap year if it is divisible by 100 but not by 400. The problem is the negation of the name. That's the value of this approach. You can tell what is wrong by looking at the name. This statement is not true of our code, but we want it to be true of our code. So if we care about driving our code with tests, however we are driving in classic test-driven approach or in a plain old unit testing approach or iterative test last, whatever, they must do more than just test that code performs its required functionality. They must clearly express that required functionality to the reader. Nat Price and Steve Freeman, who are basically the people responsible for inventing mock objects and refining our understanding of them, really make this very clear. That is, they must be clear specifications of the required functionality. Let's pick up on an observation that Phil made. Exception paths in particular can really add a lot of extra untested paths. And this is important. Leo Tolstoy wrote about this, cleverly disguised as a novel, a very long novel. All happy families are alike. Each unhappy family is unhappy in its own way. Don't just group, I see people doing things like writing tests that say test validation. Validation is not a test. Validation is a mechanism by which you by which you let good things through and you let bad things get signaled as bad and marked as bad, however you are choosing to indicate that. And there's more than one way to fail. Okay, that's the important thing. So be specific. Be as specific about your failure cases as your success cases. So if we go and look at this from an equivalence partitioning perspective, we have error cases. Some of the error cases are boundary cases, but we also have boundary cases, test at the edge. We also have simple cases. Sometimes people overlook simple cases. Oh, I don't need to test that because it's so simple. That's exactly why you need to test it. One, because it's so simple, it's easy to test. Two, guess where most bugs happen? They happen at the bit you're not looking at. You're so busy focusing on the complex bit of code that you completely forget to correct or compensate for something in the simple part of the code. The number of, I collect error screens, and the number of errors that are to do with really, really simple cases is disproportionately high with respect to how common these cases might be. So think of this is kind of like this is a Venn diagram. Venn diagram for 4 categories can actually be done in 2 dimensions. This is the shape. It's a tulip. I believe it can be done for five before you need to break into the 3rd dimension to show all the possibilities. This is your checklist, a kind of tulip of coverage. It's case coverage rather than statement coverage. Some common cases are simple. Some common cases are error cases. Some simple cases are error, and so on and so on. It's an overlapping set. Make sure you have these present. Now, let's refine our calendar. So just so you know, what we're doing here, and this is an important point because I have had this as an objection raised. Somebody said, "Oh, I don't need to have my test document what a leap year is. I can just go to Google. I can just Google it, and I can find." It's like, no, really. If that is your understanding of dates, you are exactly the target audience for this course, or this course of advice, because I think it's a fairly accurate to say that any developer who thinks they know what they need to know about date and time handling is generally wrong. Any developer who thinks they don't know what they need to know about date and time handling is generally right. Calendars are not as simple as you think they are, even if you think they're hard. They're always much harder. There are lots of different calendars. I am testing a calendar that I just made up. A few slides back, it was a universal Gregorian calendar. That does not exist. No country follows that. I made it up as a convention. But I'm now going to do something. I'm going to make our calendar specific. So it's a proleptic common era Gregorian calendar. Common era means 1 AD or 1 CE onwards. Everything before that, I am rejecting. Gregorian, that's the rule that we've just established, and proleptic, it's backdated. So in other words, yeah, this calendar has not existed for all time, and it is locale independent. I've just invented a calendar here and now. You can't go online and find that calendar because it doesn't exist, or rather, it exists inside this course. Okay, it exists whenever I run a training course and use this approach. So the point here is you can't refer to an external specification. This is the specification. Year 0 is not valid. Okay, I'm going to be very specific about that. A year is not supported if it is 0. A year is not supported if it is negative. Now, I could merge these 2 cases together, but I'm not going to because I want to highlight the 0 case. That's an edge case that people often overlook. I've even seen people debate at great length whether or not there is a year 0. The correct answer to that question is it depends, because it depends on the calendar you are following. Some people think that they are following the Gregorian calendar. Honestly, the Gregorian calendar doesn't even have a year 1. It didn't exist until the 16th century. So no, you don't need to worry about it having a year 0. The calendar that most people in the world follow does have a year 0, but most people don't know what calendar they're following. They're following the ISO 8601 calendar without even realizing it, but that has a year 0. What I'm saying here is whatever you think about year 0, we're excluding it from the calendar that is applied here. But I'm also going to logically fill out the space by saying, you know what? A year is supported. Let me just say this doesn't throw. By contrast, I'm going to show you the maximum integer. However, yeah, the way that C++ deals with traits and things like that, yeah, not so good. So I'm just going to be a little bit politically incorrect and put in max there. So what I've done is I've shown you, okay, this one is supported. There's no arbitrary upper limit. I haven't put in a magic limit. The arbitrary upper limit is the range of an int. We are basically saying this goes as high as it goes. So here we have a good specification. Right, we're done. We know 50% of what we need to know. Let's try and apply this one to something more stateful. That was a nice little example. Most people my experience, I use it as a training example. My experience is people really struggle to actually come up with a good set of tests for leap year. And that's a simple example. I like it because as an example, it highlights our assumptions. It highlights what people think they know. They think they know what the leap year is, how leap years are calculated. They think they know about calendars. Generally, they are wrong. And therefore, we are now advertising our assumptions for somebody else to come along and go, oh, that's not quite right. So what you see here is a stack of rocks. Yes, we are going to talk about one of the oldest and most overused data structures or abstract data types in the history of computer science. We can talk about stacks. Thank you, Barbara Liskov, for offering us abstract data types. This is one of the things Barbara Liskov is famous for. Many people are not sure who Liskov is in the Liskov substitution principle. This is who she is. Winner of a Turing Award 2008 or 2009, around then, for her work in programming language design and distributed systems. But we are going to focus on a stack. Here we go. Nice simple stack, not an STL stack. I'm going to use stack terminology. What I mean by that is that a stack is a thing with depth. Okay, in other words, a stack is a vertical metaphor as opposed to something like a queue, which is a horizontal metaphor. And I'm not going to use the vague term size. That's very vague and generic, and that works if you're doing vague and generic things like a generic library of containers and algorithms. But here I'm going to just use the native language of a stack. A stack has depth. You can push onto it and pop onto it. It's a strict pop, doesn't return any values, and we can query its top. And that is it. That's all I'm going to do. So we are interested in the behavior that objects exhibit, but not with any details of that behavior. Now, I can implement it a number of different ways. Here it is in terms of a vector using a pushback. Here it is in terms of a forward list. It's got different complexities here. I have to do a little bit of extra work. Here it is using a rather baroque approach based on member function pointers for internal state modeling, because a state has a life cycle. So what I'm now going to do is I'm going to separate out behavior for empty stacks from behavior for stacks. This is not a recommendation at this level, although this technique is useful for larger state machines. The key point here doesn't matter. There's no public access. So let's do something slightly different. I'm going to use catch, and I'm going to go ahead and I'm going to kind of again take my naive approach to testing. Oh, right, we're going to test. What are we going to test? Oh, we're going to test that function, the constructor, and we're going to test stack push and stack pop. It's like, yeah, you know what? We can group things a little better. I'm going to treat these as case. I'm kind of messing about a little bit here with catch's features, but let's group things. Let's be a little more stack tests. And then I've got test constructor test. Again, I don't really need to put the word test in. That's kind of redundant. We know we're testing. And here we reflect on a really common issue. We've now just boiled it down to the kind of the five operations. There's a constructor, a push, a pop, a depth, and a top. This is the most common way in which people will write tests. It's intuitive, it's obvious, it's incredibly popular, and it's completely wrong. Or it's completely unhelpful. Let's put it that way. I certainly used to use this a long, long time ago. And what I found was I agreed with every single one of my assertions. My tests, it turns out, were very thorough for a particular library that I wrote. But the organization, I might as well have just been calling it test 1, test 2, test 3. You can't test the push. Right? You can't use this properly. It doesn't make sense as a technique. The idea that you're testing a member function and not using the others doesn't make sense. In order to test push, I must construct an object. In order to test that my push is successful, I need to then interrogate and ask my stack various questions. Hey, your size should be 1 greater, and your top should be the thing I just pushed. So in other words, in order to test push, I will use 4 of the 5 available operations. So is that testing push, or is that test? In other words, it's the wrong point of view. Also, by saying I am testing the constructor, it suggests that I must write a constructor. The chances are, if I write stack, honestly, I don't need to put this in. Stack equals default. Okay, basically the constructor synthesized by the compiler will be good enough. Okay, that's fine. So does that mean that I'm testing the compiler now? Test the constructor, is that testing the compiler? So therefore I should remove it? So at this point, what we've discovered is that our tests are brittle because they are now dependent on what I have written rather than what I can use. We should focus on capability. So some people jump into this smell. And yeah, this is a smell. They talk about can be something and has something. That's a kind of workaround for I'm testing by member function. Yeah? So that the common smell here, so you recognize it in your code and in the code of others, is I have for every function that I have a corresponding test function. It's a one-to-one relationship. If you have a one-to-one relationship, guess what? You have work to do. That's great. Yeah? You have something you can learn and improve in the code. Also, these statements are untrue. They are false because the API that I just gave suggests that you can pop an empty stack. I'm going to say, no, we're having exceptions. It suggests that you can ask for the top of an empty stack. That's not true. Which now leaves us with these incredibly vague names. Yeah, could sometimes be popped, sometimes has a top. Now, this is just vague. Okay, so we need to move to a much more specification-oriented approach. Let's think about this as a spec. Let us use this as if it were a thing, a piece of software to be tested. Given an empty stack, when an item is pushed, then it is not empty. Okay, that's a start. It's a little bit vague, though. I mean, it's not that this is false. It is true, but it's not the whole truth. It's not empty, yeah. But there's lots of cases of not empty. Be more precise, okay? One of the things you need to negotiate is the strength of a test. Sometimes people overcouple their tests to their implementation. Their tests are too strong, but sometimes they undercouple. This is an underfitting test. It has a depth. It has, basically we're saying its depth is greater than 0. What, 5? Is 5 correct? If the depth is 5, is this? No. There's only one right answer. Okay, one right answer, and that is 1. All other answers are wrong. We're still not being precise enough, though. The top item is the item that was pushed. There we go. So we can take, so given when then gives us a nice structure, a 3-part structure. It's like precondition, operation, postcondition, okay? And it's a structure that tells a story, past, present, and future. It's a narrative we can see that is useful for understanding functional requirements, but it is also useful for interrogating and understanding and reasoning about pieces of code. This idea of precondition, operation, postcondition dates back to 1969. That's how old the idea is. So I can mash all of that together. I can probably do better and put underscores in. If you're using catch, guess what? You can use strings, much better, okay? And yeah, you don't, if the given when then helps you, go for it. If that moves you in the right direction, go for it. But you will find that sometimes, you're able, it's a guideline. It helps you move in the right direction. The English is simpler. I've got a question from, it's not empty. Can say it is not empty. It has a depth 1, right? Abel asks, do you even need to know the stack is empty and the size after push? Yes. Otherwise, what are you talking? You're not even talking about a stack. Well, how do you know that it's a stack? You know, oh, I pushed onto it. What can you tell me about it? I can tell you nothing about it. Okay, I've just found a problem with your design. A stack that you cannot find out whether or not it is empty is not a stack. It's a magic box where things happen in an arbitrary fashion. So yeah, you need that. Otherwise, you don't have a reasoned model. So yeah, you only need to know after the push the top of the stack of the pushed item? No, because it could just be a replaced item. You know, it could just be a variable. It could just be an optional. Effectively, I could just be wrapping an optional. So that's the key thing. Yeah, sorry that if I jumped onto that one. The second sentence. What great depth. No, Benjamin has made the observation, I honestly cannot picture myself standing in front of stacks of colored rocks and thinking to myself, what a great depth these have. Great is a quality judgment that is outside the scope of my tests. Seems a strange term to use. In that case, those stacks of rocks, it's a vertical concept. The orientation is, in that case, it is a vertical orientation, so height would be the appropriate one. However, I did not have a handy photograph that I had taken of a push-down stack, so I've used that. But at least it has a vertical orientation, so I hope that clarifies things. Either way, what we're moving towards is omit needless words. So what can we do? We've got a nice specification here. We have got a simple idea of a structure. A new stack is empty. An empty stack throws when queried for its top item. An empty stack throws when popped. An empty stack acquires depth by retaining pushed item as its top. In other words, we've got a full dialogue. This is a really nice description. This is a specification. Okay. Now, we can do, there's a couple of things that we can do here. So here in this sense, let me just tweak a couple of things. I can structure the insides of the test in terms of this idea of a kind of a given when then, but also in terms of a range act assert. People often try to talk about it in those terms. And Jeremy Mazaris sort of talks about this, describe the context, the starting point, or the preconditions, illustrate how the software is invoked, and describe the expected result or the postconditions to be verified. So a range act assert or given when then, these are equivalent at this point. But let's kind of close in. Thinking in states, let's talk about this observation. In most real-world situations, people's relaxed attitude to state is not an issue. Nicholas Nielsen highlights this problem that I've noticed is a very common one. People kind of look at the data members, but they don't really understand the interactions and the life cycle. What is the code supposed to do in different states? Unfortunately, however, many programs are quite vague about state too, and that is a problem. So let's understand the state model of my stack. It's a life cycle model, empty, non-empty. I can push, I can pop. In the empty state, I don't have we might say, oh, it's undefined whether or not I can top and pop it, but top and pop are applicable in the non-empty state. When you pop a non-empty, it remains non-empty if the depth is greater than 1, but it becomes empty if the depth is 1. The behavior is not actually undefined. We have a very specific mapping of it, and so therefore we have a structure here that we can use. So I can actually use that by nesting. I can reflect that in my test cases. This is the bit, the refinement, if you like, that people often miss. The idea that when we say, you know what, this should be like a spec, when we say that, what we mean is this should be like a spec. It's not a kind of figure. It's not just a turn of phrase or a figurative thing. We actually mean it. We're quite serious. This is what we want it to look like. Yeah, this is kind of the structure. Okay, a new stack is empty. An empty stack throws when queried for its top item, and so on. And what is interesting about this one is that this one is a much better specification. Some people are looking forward to C++23, which will have C++23 will have programming by contract, which allows you to do almost nothing useful and will not be able to, it will never ever be able to rival the specification level of a test. Particularly in C++23, the design by contract mechanism is so weak that you can't even specify the basics of a stack. That it's not very useful. Whereas here we've actually communicated intent in a way that is executable and checkable. So what else do we want? Well, I can also move out common state, and I can abstract out common state, common givens, if you like. Now that's kind of an interesting one because that also suggests, so I can move things around, but it also suggests that I can use the given when then approach to factor out the structure of my tests. Given things with common state can be a way of structuring your tests. It defines the hierarchy of your testing. Alternatively, common action. When pushing, maybe I want to communicate to the reader something different. When pushing and when popping, and therefore my main emphasis is not state, but action. Or I can organize it by outcome, which is what we did for the leap year case. And I'll just close with a consideration of another data structure. And you go, well, yeah, this one, if you thought the stacks was tenuous with rocks, this is even more tenuous. This is a queue of drinks. I mean, the queue of drinks when I was younger, this is me and my co-author Frank Bushman and Mitchie Henning. I was younger and we could drink a lot more. These days, it's as much as I can do to drink that. Yeah, Phil says, we hope C++23 will have contracts. Honestly, I don't hope that it will. I think the contract model is so defanged, it's entirely useless. There's a lot of people who've never tried contract programming and they think it's a cool idea because it looks good on paper. Honestly, in the early 1990s, or when I first read about it 30 years ago, was when I first put it into practice. It's the first article I ever published was on contract programming, and I thought it was a good idea. And then after a few years of usage, I realized what its limitations were and what you really needed. And let's put it this way, the stuff that's coming out in C++23, that's not what you need. It's a really powerful thinking model. It informs tests, but the way that it's done in C++, not going to work. It's just not even worth the effort. So I'm not going to draw, though there's a whole, I'm on the, close enough, but no closer in terms of the committee. Right, so let's talk about a queue. We're going to use this as the closing example, and then I'm going to ask Tom's excellent question, unless anybody else has other questions as well. A queue has a bounded capacity. We're basically going to go with that. It's got a length. It's a horizontal metaphor. You can enqueue and you can dequeue. I've got no exception conditions. It's perfectly fine to enqueue when it's full. You just get false and it says, I did not enqueue. You are always entitled to attempt it. It is not an error mode. It is just an operation that may, you know what, come back later. Dequeue is always successful. It either returns the value that you dequeued or it says, I'm sorry, there was nothing available at this point. In other words, it's a normal operation. It's not an exception. The structure, we have a producer, consumer. However you think about queues, they are ultimately space-time decouplings. We are going to make sure that they are also not, they're not empty. You need at least one item for it to be a queue. And you might think, yeah, we saw this a few slides ago, Kevlin. This is like the stack, isn't it? It's like, yes, except no. This is more involved. It's not just that it's non-empty. When it's non-empty, it can be non-full or full. It has different behaviors when it's full. When you try and enqueue on a full thing, then it doesn't enqueue. You remain full. Right, okay, so that becomes an important distinction. And we can also reflect that hierarchy. Notice that hierarchy, that nesting in the state model is visible in my tests. A non-empty queue that is not full becomes longer when value enqueued. A non-empty queue that is not full becomes full when enqueued up to capacity. A non-empty queue that is full ignores further enqueued values. A non-empty queue that is full becomes non-full when dequeued. This is what we mean by this. So that idea is quite key. We want to move from the kind of 1970s view, epitomized by Nicholas Wirth, algorithms plus data structures equals programs, to a much more kind of like 1980s onwards view, but really try and take that into our code. Structure plus interpretation is programs. And some of the interpretation comes from within the code. But I want to try and make sure that we are able to separate our concerns and articulate how something is used. Let us specify the behavior, but in a way that people actually pay attention to and take care of. It turns out that if you write a comment that is wrong, nothing happens. If you write a test that is wrong, people get rather upset that you broke the build. Something happens. So we need to move all of those other ideas that we have. We're never short of ideas, but we need to learn to articulate those and put them somewhere that people will care about them. So, the question from Tom, curious to hear what your advice is when trying to follow the tell, don't ask OO principle when it comes to testing. Make sure some state accessible seems to be the best option, even if it compromises. I don't regard the tell, don't, I don't regard that as an OO principle. So that's how I solve that problem. I understand your objects. What do they want? I've got encapsulated state. Okay, what is observable? That's what I don't think in terms of, are my data members public, or is that I say, what is it that I can do with this thing? In other words, I follow object orientation. The tell, don't ask thing, that's kind of came along later, and it's encouraged a lot of people to turn to put mocks everywhere. I do not regard that as a founding principle of OO for the simple reason it was not a founding principle of OO. The founding principles of OO are a little bit simpler. Here is a thing. What can you do with it? That's pretty much it, okay? When you do something to it, does something else happen? That's where you start talking about tell, don't ask. But that's not a principle. A principle is something that applies universally. Most of the things people call principles are not principles. Solid principles especially are not principles. They're a couple of good ideas and some misunderstandings, but they are certainly not universal. Tell, don't ask, not a principle. Useful in some cases, but in other words, what can I do with this thing? Describe the capabilities of this object. Let us talk about those. That's it. Don't couple yourself to private implementation detail that can change. Okay. In other words, things that are not important should not be coupled to. That's why we care about private. Encapsulation is not also just about visibility. It is also about capability. What do I need to know in order to use this? So the problem just kind of disappears. The interaction testing that comes about because people get obsessed with tell, don't ask because they think it's a principle. It's not a principle, people. It's an idea that sometimes is useful. Oh, wait a minute, we call those patterns, yeah? In other words, certain things are well solved in certain contexts. In other cases, these are just queries. Objects being queried for behavior is absolutely fine. There is nothing wrong with that. And anybody that tells you so, send them in my direction, okay? I'll set them straight. Question from Ryan. Do I have recommendations for making complex data unit testable, specifically 3D or 2D image data that is not easily boiled down to a metric? That is a nice, big, open-ended question. Do I have recommendations? Yes, none that will fill the next 30 seconds because I recognize I am over time. I would need to know more about the nature of the data. So, for example, one interesting example would be you've got a very particular model here that you're focusing on complex data, image data. Let me just talk about raw images for a moment as opposed to constructed images. A raw image, so let's say we do some image processing. I do not want to assert on every pixel, okay? Hey, I took an image, and let's say we're doing an edge detection algorithm. I took an image, and how do I assert that the result is correct? Do I know every pixel in advance? No, I don't. Okay. This is where we have to get into a little bit of a dance with what we're doing. We have to say, right, one technique would be to use an approval testing approach. Approval testing is basically, let's run the algorithm and let's get a domain expert. Maybe that's ourselves, maybe it's somebody else, maybe we're doing our image processing for the medical domain, for example, and perhaps we have an expert on hand. We can do, is this what you'd expect? Yes, okay, that becomes a stock. You know, that becomes a kind of like a master record. And so therefore we say, yeah, this is our gold standard. And then we assert against that. Problem with that, however, is that that is brittle. Let us say we improve our edge detection algorithm. It's much better, and then we run the test. It fails. Does it fail because the code is wrong? No, it fails because the code is good. The code is even better than it was before. We made our test too brittle. So what we need to do is that gets us thinking, what are the qualities? And that's why this is an open-ended answer, I'm afraid, Ryan. We need to figure out what is it that constitutes a well-defined image processed structure or a good edge detection. Perhaps contrast is part of it. Perhaps approximate distance to the idealized edge detection. So for example, if you have an image, then you have an idealized, you can draw a wireframe and say, this is the idealized version of this. And what we do is we measure distance from that and we define what is acceptable criteria. So in other words, you have to approach it from a slightly different angle. It's no longer this equals that because I knew the answer in advance. Sometimes I have to determine an answer and then understand what my tolerances are. But what I'm now looking for is qualities that I can assert on. And distance from a known image or an idealized image might be an approach there. Benjamin's question, also quite open-ended. Any recommendations for which framework to pick or start out with? Disadvantages regarding. Okay, for C++, I'm going to go. My recommendations are generally Google Test and Catch. Those have wide support. Google Test in particular, clearly a lot of support. Catch, I have a slight bias to. Phil developed it, built off the back of a set of ideas that I presented in a prototype, a testing framework a few years ago. I like its universality in terms of arbitrary depth nesting, the ability to use free text effectively to describe the testing structure. I tend to bias towards those. I haven't used Boost Test for a few years. Maybe that's come on a bit. It used to be a bit better. I would absolutely avoid CppUnit. That's kind of a few opinions there. Let me pick up. Doc Test. Thank you very much for mentioning that, Tom. I have not looked at that. I've had a number of people recommend it to me. It's kind of as being associated. I do get confused sometimes unless the context is clear when people say doc test, because I really do wish people would actually do a Google search on the names of things before they named things. DocTest is also the name of a Python testing framework which has been around for much longer. So I was initially massively confused when somebody a while back started talking to me about DocTest, and I said, yeah, I've used DocTest. And then I thought, what's that got to do with C++? Yeah, so please, people, if you're going to write a testing framework, do a Google test first. That's the first test. And that Google test is not Google test, it's Google test of your framework. Other comment from Tom, one thing I found is breaking down types through composition can then test those things more easily in isolation, which helps. Yes, exactly. Encourages you to break apart. The idea is to encourage a compositional approach, whether we're looking at functions or whether we're looking at objects. Break it down into the parts. These parts are more easily testable. I put them together, I get behavior I'm expecting, and so on. It's a compositional approach. That's really where we want to go. Okay, so we really need to wrap up, says Phil. Damn, he is right. And I am traditional in overrunning. So apologies for the overrun. I hope that's been of some help. My contact details are conveniently stated in my name. You can normally find me online. Find me on LinkedIn if you want to do any follow-up. You can also find me on Twitter. I hope that's been useful, and hope to meet you all at some point in the real world. Have a good one.